All right, I'm doing one of those stand-up comedian-style lightning talks because it was just this morning when he said that there's still slots left and work and project is welcome. So I thought I'll just do something and let's see where this is going. So I want to talk about laziness and something that we Haskellers like to boost and think it's great and you can solve many interesting things with it. And one really good example for like a nice idiom for using laziness is calculating the transitive closure of a graph. So here I'm defining a graph type. It's a map from vertices to the list of successive vertices. And now I maybe need to define the transitive closure of that. So from each vertex, which other vertices can I reach? And the beautiful thing we can do in Haskell, because we're lazy, is that we can do a knot tying trick where we like this map here is like the result that we want. And you can actually use that map in its own definition. So I can write that like the sets of reachable vertices from each vertex is, I go through the graph, I look at each of the elements together with their successors, and then what are the reachable nodes from vertex V with successors Vs? Well, it certainly is itself. And then also the union, the big union of all the possible, well, let's look at all the possible vertices reachable from this. And now I need to, well, find all the things reachable from the successors. And there I can actually now just use the set that or the map that I'm defining right now. I'm sure most of you have seen code like this before. And it's quite nice and impressive. And let's actually get a graph that we can run this on. And let's see that it works. So here I define a simple graph. It has 3 nodes. 1 goes to 3, 2 goes to 1 and 3, 3 goes nowhere. And I can run this and it calculates the transitive closure. Ooh, the audience is impressed. With the exception of there's one person in the audience who will always come up and say, like, what happens if you have a cyclic graph? So let's try this. I mean, we have a nice algorithm. Let's make it cyclic. Let's say from 1 I also go to 2. So now you see it's cyclic. 1 goes to 2, 2 goes to 1, and they all goes to 3. And now I reload and pass this to graph 2, and suddenly our Haskell program doesn't look so nice anymore. That's just embarrassing. And in a way, this comes often that you have these nice idioms with like laziness and recursive definitions, and they kind of work well for toy examples. They sometimes work well for real examples, but you often hit this like limit where you can't make more progress. And then what you do is you I don't know, you write code like this. Like, I don't know how often I've written a loop called go with a scene argument when I was doing mostly like recreational programming, but also in practical thing. Like it comes up, and this is not declarative. This is like a while loop. That's not what I want to write. So wouldn't it be great if you could just write the code that we have up here, like with very declarative definition of things, and still get the right result? And I claim you can. So for that, I need to import a different library, which is relatively new. And then I can take this code, and really I just have to change a few types. So instead of R set, I have to change the name, I guess. I'm using this recursive set thing, and then I have to adjust a few things. So, well, before I get the list out of it, I have to get it out of the R thing. And then here, of course, I have to use different operators here, but they're the same, like insert, unions. It's pretty much the same code. Okay, let's see. So let's make it exciting. Let's start with the first graph. So this was transitive 1 on the first graph, and now we can use transitive 3, and hey, it gives the same result. And now let's try another graph, and it works. Right, so this is work in progress. I noticed that it is possible to define a data type that behaves like this. The implementation is not normal Haskell. So if you look there, you'll find things like unsafe perform error and things. But my claim is that the interface that we have here, and just to summarize them, this is the interface I'm using. So it's really very much similar to the normal set interface. I claim that the interface is still pure safe Haskell that you would expect. So just for like to make the drive the point home a little bit more, I can provide something like the set S is well, I'm inserting the number 42. Oh, let's use 2002. It's in the set S, and then I can get the set out of this thing, and it works. And this is something we're used to these things when it comes to constructors, like cyclic lists. We can work with that, but we haven't seen that much with like other stuff. And I really wonder why haven't we seen that? Because it seems so useful. It seems safe and pure, at least in the interface. And we're used to using libraries that have an unsafe inside, but provide a safe interface around. That's something we've come to terms with. So I'm a bit surprised that I haven't seen much of this before. So I'm wondering if I'm just missing something that's completely broken. And then of course there's a question like, what does it actually mean to be safe and pure? There's no definition I can look up really. I mean, there's definition like referential equality, but that holds. Like if I can take the right-hand side of S here and put it in here, and still get this. Well, sorry, still get the same result. So I can still rewrite with equalities. That's kind of referential transparency. There are other things that I can't do anymore. For example, if we start with this again, before that, I think this would always be a valid transformation, where we take the value S and we turn it into a function that takes an argument, could be a unit, could be anything else. Now this no longer becomes productive. So static argument transformation suddenly can make programs become more defined. Is this bad? Is this something that rules out the whole thing and means this is no longer something we want to see as pure API in Haskell? Or is that a transformation that we kind of accept to possibly change the definedness of things? Because, for example, the compiler wouldn't do this transformation on its own without good reason, because it will definitely change runtime performance. So maybe this is it's okay to not have this. And this is a discussion that I want to start here. So the libraries on Hackett, there are 2 blog posts about it on my webpage, one about the user-facing interface, one about the implementation. You have sets, bools, and you can define your sets this way, and they should give you a result even if your definition is recursive. And yeah, this is what I'm currently working on. I hope maybe next year I'll be here with like a 20-minute talk at one of the real serious things, but there are a few open questions until then. And I'm happy to have a discussion about that here. So thank you.
Hello, I have the mic. I win. Yes, so there's a paper, I think like at least 5 years ago, from François Potier, where he said something like this in OCaml. So quite similarly, it uses references and all kind of mutations under the hood, and has some pure interface for recursive equations. We can look for it together later if you want. I don't remember how the paper is called. So I think it ends with a challenge that will be familiar to you, which is prove that the interface is indeed pure.
Right. So speaking, I think somebody mentioned that to me, and what they do is actually stronger than what I am aiming for here. Like they allow you to even define functions that consume cyclic data and still be productive. Like you have a cyclic list and you map over it and you still get a cyclic list out. Or you have a cyclic list and you do something like this with like you map it into a set of equations between sets and you get that thing. So that's even more impressive. But I think somebody pointed out that's not referential transparent anymore, but I'm not quite sure. So this is definitely related work that's relevant to look at. In terms of proving, just to hijack the question, I think the only place I've seen in the Haskell context, at least, where somebody proved something to be pure is the proof that runst is pure, which is, or at least that's like where you, or that's maybe the most prominent example where I've seen. So the ST monad is supposedly safe because runst does this nice trick, and we didn't know that this was safe for like 20 years or so. And then somebody made an interesting complex proof with logical relations. But I think only in the like non-threaded case. Now I'm using unsafe IO. That's like concurrency, but just worse. So I wouldn't even know how to. I wouldn't know what to prove, and I wouldn't know how to prove it. So there's stuff to do.
Yeah, so one of the things that I would expect with purity is that data structures are persistent in the sense that you can have some set and insert some stuff into it, and then insert some more stuff, and then have two sets which you can both inspect, and one will be the subset of the other. Do you get? Sorry. So S0 is stuff, and then S1 is insert some stuff into S0, and then S2 is insert some stuff into S1. Can you then both do get R on S1 and on S2 and get sensible results?
Yes. You can use get R on anything that you have that has this type, and it shouldn't matter whether like which order they get evaluated and things. It shouldn't matter if you like use one of these R things somewhere else. Shouldn't affect what you read out of it. That's my claim at the moment. Oh, I let this run. That's why my laptop became so slow. Okay, maybe it'll recover.
Is it thread safe?
So that was interesting. At first I thought it would be probably. And then I found a really great library that's maybe underused. It's Deja Vu, which allows you to, like, you write your code in a overloaded monad, and then they basically explore all the schedules and notice, oh, this isn't thread safe. And then I spend a lot of time trying to figure out what possible order of mvars, take mvar things might make it thread safe. I believe, well, let's see, I'm optimistic at the moment that it's thread safe. Like the test that I wrote seemed to say that it's thread safe. The thing that I'm worried about is because, I mean, use unsafe perform IO, it's not just thread safety, but it's also like reentrancy of the same thread. And maybe there are cases where you can run into problems right now if you use getar inside the definition of the whole thing, or maybe we're safe the way it works. Like this is something that I need to still figure out more, and I'm happy to have people poke holes in it and tell me where it breaks. But yeah, the Deja''vu library is really useful. So I can show you the tests while people think of the next question.
I have a question.
Yeah, I'm ready. Yeah.
Can you just describe from like a very high level what the unsafe perform IO is used to do?
Sure.
And why it needs to, it can't just be pure.
Right. Oh, well, it can't be pure. Okay, that's a good question. Like, why can't it even be pure? I think there might be a simple argument saying like it needs to be lazy because you need to build these recursive things. But if it's lazy, then and you don't do anything else magically, then you can't really get anything out of it. Like there might be a high-level argument why, like there isn't a pure implementation that actually works, or maybe there is for some data types where you make them very like try-like. So what I'm doing below is that. Well, I'll jump to the like this is the gist of the implementation. So these R values, they contain a cell, and a cell I'm deferring to like a whole. Like imagine there's an IO library doing kind of setting up a graph, setting up relations between the cells in the graph and solving them. We can imagine that being done by somebody else, and that's done. Like the IO part, you can do lots of optimizations there, but that's not the interesting part right now. And what I want to do is want to wrap it in this pure thing. So I need to put this mutable cell that does the propagation inside in the data structure, and then we have a few minutes. So let's start with this code. So naively, I might do something like, okay, if I want to define a new set that's X inserted into some other set, I create one of these new cells in the underlying imperative graph declaration library. And then, oh no, this is the code I want to show. Okay, sorry, this is a simple code. So I create a new cell, I declare to that library, this cell should be, like cell C1 should be C2 added with X. And then I return the cell, and then I just use unsafe perform IO around get cell, and that looks reasonable. So this is really just naively taking the IO library that might exist and turning it into a pure thing. But this doesn't work because it's too strict. So the thing here is that because I want to build these recursive equations, I need to get my hands on this C1 to pass it to one of the other insert functions before actually using these C1s, but I guess the other cell here. But declare insert in the underlying IO library is probably strict, so this will be strict and won't work. So really, I need to make sure I get to return the C1 before I do actually declare the relations to the underlying infrastructure. So I could try to make it like just use normal laziness and put this into an action that I run later. I run it actually when I'm querying the result. But this doesn't work because you need to actually run all the things of all the related cells. So you kind of need to have some infrastructure to say, here's an IO action, run it later when I tell you to. And when I ask you to run this action, also run these other actions, and they can refer to each other recursively and make sure you don't run in cycles. And this is, and if you have a helper for that, then the code looks very similar to what we just saw, just that the func is a bit more explicit. So what's happening here is that I create the cell in the library. I remember that I have to register the relation to the other cell, and notice that the C2, which comes out of the R2, is not used until we actually run this func thing, which means that the function is lazy in the second argument. Which means you can actually write the recursive thing and make progress. So that's the first step. And then when I actually want to get the value, I have to tell this library that manages the funcs to now run the thing. And running the thing not just means running the declare insert for this particular cell, but it also tells you also run the things related to this other thing. And then there's like, I like to put these things in very specificalized compartmentalized APIs. It also makes sure that if you have these funcs referring to each other, then you don't run in cycles, but you just make sure everything runs once in some arbitrary order. And this is really the main tricks. And then all the problems about like thread safety and things are delegated to these sub-components, like the thing that solves the equations and the thing that makes sure that we run all the registration functions in time. And hopefully that's thread safe. And yeah, hopefully that kind of sheds a light in what I'm doing here.
Yeah, I think that definitely helps. I mean, I'd have to think about it a lot more to understand sort of what specifically, I mean, obviously you'd have to express it in a different way, but whether or not it would be possible to express, like, as you said, maybe using some kind of try data structure or something, but it's very interesting. Obviously it looks like you have a blog post about this, so I can just read that.
No, but actually the question is really good. Like, why don't we just write pure code? And I think it's not possible, but I should come up with a good argument why I think it's not possible.
Yeah.
Or maybe the argument could be the following. If it was pure code, then at least, unless I'm mistaken, I could just unroll the whole graph and still get the same result. Like with a cyclic list. A cyclic list that you do use with not tying is indistinguishable from a cyclic list that is not done with not tying, but rather just expands memory, at least until you hit the end of memory. And that is a property of like normal Haskell, pure Haskell. And with something like this, I think you can make an argument that if you don't know the recursive structure, you just explore it by unrolling, you will not be able to find a solution. Therefore, pure code is impossible. But I'm making things up, I understand. So, but yeah, thanks for the question.
Is there some kind of monotonicity requirement on the algorithms that you can do with this?
Right. So I guess I didn't highlight that. So the idea, you don't get to just use arbitrary functions when you like define these things. So x equals not y and y equals not x is a solution. X equals not x, that will not give you a solution. And that is precisely that. You need to can only combine functions that work well together by being monotonic in the same order on the values. So that's why the data recursive set module has things like insert, delete, filter, unions, intersection, member, not member, disjoint. But for example, it doesn't have difference, because if you like taking set s minus set 2 as minus set s2, if this one gets larger, then this one gets smaller, and then you can have equations that don't really find a solution. But the idea is here that I'm not exposing every function on sets, in this library, but only those functions that I know are safe to use. But then I get a safe interface.
Okay, but then have you had situations where there were like two sets of functions you could expose, but not both at the same time? And then are you like overfitting to the motivating problem? Or?
So one example where that, well, actually it's not the same set of functions, but maybe that's related. So the Boolean type is another good example for, this is actually the practical use case where I wanted to use this. Like a simple flag. I was also writing a compiler analysis to find out, can I allocate these things in static memory? And of course, with recursive things, that depends on whether I can put all the other things it refers to in static memory. So I needed to have a recursive thing and the language of recursion. So I wish I had this code back then. Well, it was also a camel, so it was different, but anyway. So this is where the idea comes from. So Booleans are just a simple example for the things you can do. But there the question is, do you want the least or do you want the largest solution? Do you prefer true or do you prefer false? And the way I solved it here is that, well, if you use R of bool, then you get the least solution. And if you use R of dual bool, you get the greatest solution. And they're not isolated. So for example, the not function will of course go from one to the other. So you can mix these things. You can also mix bool and set. And if you look at this at the set API, where is it? Then we see that some functions like member goes to bool and not member goes to dual bool. So you're not in a silo for specific partial order that you're choosing. And maybe what you want to express is possible if you mix like different orders in the same types by using new types or some other trick. Does that answer the question? More or less, a little bit. Yeah, it is not nice that you have to like predefine all the valid functions. And if you had liquid Haskell in GHC already and fully embedded, I could have a pure like a general interface for this whole thing that just says, take any function where you have a liquid Haskell proof that is monotone, and then the user could just write any code, and the type checker would, the liquid Haskell type checker would ensure that you get a unique result and these things. So that might be something for the glorious future.
Would it be possible to wrap it in some sort of monadic interface so that some transformations, we wouldn't expect it to remain referentially transparent?
It would be, but I think that's precisely what I want to go away from. So there are libraries that do similar things that have a monadic interface. Elvish is one that keeps being pointed to me. Also, if you're in a monad, then doing this kind of bookkeeping of have I visited this node already becomes less annoying. The point here is really, and I guess, well, maybe like this kind of code down here, you could imagine that being a monad and then it becomes a bit nicer. But really the point is I don't want it to be a monad. And R is not a monad. It's really just a wrapper you can just extract things out, which is precisely what you can't do with monads often, like usually, like not in this way. So the idea is that it's precisely not monadic. I want to do pure code that just explains the graph of your equations and you get a solution. Like to me, pure is always better than monadic. I keep writing code in pure style as long as I can, and maybe add parameters before I go to reader because I don't want a monad. And then eventually, always there's something they need a monad, and then you can just pile the monad stack, of course. All right. Well, thanks for the attention. It's on Hackage. Play around with it, break it. Tell me how you break it, and maybe there's more from me about that later.